Hi everyone, so this is chapter 1.1, proof by contradiction, part 2. So I'm going to do the example 3 and 4 in this video. But before we do that, we are just going to recap the definition of rational and irrational numbers, because lots of proofs involve proving certain things are rational or irrational or whatever. So just to recap, a rational number can be written as a over b, so i.e. it can be written as a fraction, where a and b are integers and they do not share a common factor. Now this extra bit is not in the textbook, I've added this on. It's very important for the proofs that we do, but it's not actually written down in the little bold type in the textbook. So make sure you get this bit down. That a and b, they are integers and they do not share a common factor. So for example, a and b cannot be 4 and 6 because they share a common factor of 2. Or it couldn't be 8 and 20 because they share a common factor of 4. This means that a over b is in simplified form. So essentially, to kind of write this in kind of quick form and slightly easier to remember, a rational number can be written as a simplified fraction and an irrational number cannot be written as a simplified fraction. That's essentially what they are. But this is the official definition. So a rational number can be written as a over b, where a and b are integers and do not share a common factor. In essence, a over b is in simplified form. So, we can now go on to example 3 because we've just recapped the definition of a rational number. And example 3, we want to prove by contradiction that root 2 is an irrational number. So we want to prove that the square root of 2 cannot be written as a simplified fraction. Okay, so if we remember step 1 from our previous video, step 1 is to make your assumption. And remember, you're going to assume that this is not true. So actually we're going to assume that root 2 is a rational number. And remember, from our definition, this means we can write the square root of 2 as a over b, and you can pick any letters, where a and b are integers that do not share a common factor. That last bit is really important. Okay? So, we've made our assumption. We've assumed that root 2 is rational. We've assumed that it can be written as a over b where a and b are integers and don't share a common factor. So, we've assumed this, right? That root 2 is equal to a over b. Now, if I square both sides, then I get myself 2 equals a squared over b squared. So remember, step 2 is where you complete your algebra, and you complete your algebra to a point where you are trying to show that this statement is impossible, this assumption is impossible, or it contradicts itself. So I've squared both sides anyway, and what I'm going to do is multiply both sides by b squared to get that 2b squared is equal to a squared. Now, this statement here, that a squared is equal to 2b squared, means that a squared must be even, right? Because a squared is equal to 2 multiplied by something. So I'm going to state that. So a squared must be an even number. And in example 2, in the previous video, we did a proof that's, we proved that if n squared is even, then n must also be even. So because a squared is even, a must also be even. Trying to make this sentence make sense. A squared must be even, so a is also even. Okay, so a is an even number. So if a is even, we can express it as 2n. So a equals 2n, 2 multiplied by some other number. We should state that n is an integer. So just to recap, we squared both sides to get a squared over b squared equals 2. Then we multiplied by b squared to get this statement. And this statement shows that a squared must be an even number. So because a squared is even, a must also be even. And if a is even, it can be expressed as 2 multiplied by some other integer. Okay. So now what we're going to do is substitute that into this expression here. So we are going to get that 2b squared, so if I put a little star next to this, I'm using this statement here, 2b squared is equal to 2n all squared. Just going to multiply this out, so 2b squared is equal to 4n squared. And then dividing by 2 both sides, we get that b squared equals 2n all squared. And this means that b squared is an even number too. Because b squared is equal to 2 multiplied by something. Okay. So b squared must be even too. So b is also even. So, 2 really important statements in this proof is that a is an even number and b is an even number. We've shown that a and b are both even. Now if a and b are both even, they share a common factor, don't they? They share a common factor of 2. And that contradicts our original assumption. Our original assumption is that root 2 is a rational number, which means we can write root 2 as a over b, where a and b are integers and do not share a common factor. We wanted a over b to be in simplified form. They should not share a common factor. And with our algebra, we have just shown that a and b are both even numbers and they do share a common factor. So we are ready to do step 3 now of our proof. So we would say, just using our sentence frame, I'm going to look back to example 1. So the assumption that root 2 is a rational number can be written as a over b in simplified form. F-I-E-D. is not true. Because A and B are both even, i.e. they share a common factor. And the last part, step 4, is just to state that our original statement was true. Okay, so step 4 is therefore root 2 must be irrational. Because when we assume that it's rational and we work through our algebra, we get a contradiction in the algebra, and that's not possible. So just to highlight the steps that we went through, we were given the statement that root 2 is an irrational number. We assumed that that was not true. We assumed the opposite. We assumed that it's rational, that it can be written as a simplified fraction, a over b. And so A and B do not share a common factor. We worked through our algebra and proved that A is an even number and B is an even number. And that's relevant because if they're both even, then they share a common factor, which contradicted this part of our statement, that they do not share a common factor. Then we just use the sentence frame to state that, so the assumption blah 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 is not true because. So we're kind of explaining what we found there in the algebra, and then the last step is explaining or just writing that our original statement was true. So that's example 3. Example 4. Example 4 statement is proved by contradiction that there are infinitely many prime numbers. So we want to prove that there is no end to the prime numbers, that there is always a greater prime number than the last one that we have. So we start with step 1 by making an assumption. And we are going to assume the opposite. We're going to assume that there's a finite number of prime numbers, that there is a final prime number. Okay, so we're going to assume there's a finite number of prime numbers, that there is a final prime number. Step 2, we're going to start doing the algebra. So, if there's a finite number of prime numbers, we should be able to write them all out in a list, right? So we're going to list all the primes. Obviously we're not going to do that. We're going to call the first prime P1, P2, P3, so these are all the prime numbers, 2, 3, 5, etc, 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 and because there's a finite number, there's going to be this last one. This is under our assumption. So there's a last prime number, a final prime number. Now, we're going to consider another number. N, capital N. Now, I'm going to decide that this capital number N, I create it by multiplying my prime numbers together. And then adding 1. So there's this other number, I'm saying, in the world, in the universe, that I create by multiplying all of these primes together, and then I just add 1 to it. So this is just another number. Now, when I divide n by any of the primes, so P1 or P2 or P3, etc., you get a remainder. Of 1. So this means none of the prime numbers are a factor of n. So essentially what we're doing here is, if I decided to do n divided by P1, this is what I would get. I would, because I've divided by P1, this would be cancelled out, and I would just get P2 multiplied by P3 multiplied by blah 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 up to the final prime number plus 1. So we will still have this plus 1 remainder here. We'll have all of these multiplied together plus 1. And you could do that with any of the primes. And that means, because you have this remainder, that means that none of these prime numbers are a factor of this, because you always get something left over. They don't divide into it perfectly. So, this leads us to another conclusion, or to a conclusion, that n must either be prime itself, because or have a prime factor, which is not in the list, P1 to Pn, which is all the prime, which I stated at the beginning is all the prime numbers. So, just to recap that, when we took this number n, which is just a number that I created by multiplying all my primes together and adding 1, it's just a number in the universe that exists, and I divided it by one of the primes, I get this remainder of 1, which means none of the primes divide perfectly into n. And that means if there's a number where there's no other number that divides perfectly into it, apart from itself or 1, it must be prime itself. Or maybe there is a prime number that divides into it, but that prime number isn't in that list. But we just said this is the list of all the primes. So that's your contradiction. Okay? So we can say, just using our sentence frame, so the assumption, remember our assumption was that there's a finite number of primes, prime numbers P1 to Pn is not true, because there is a number capital N where n equals P1 times P2 times blah 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 Pn plus 1, that is prime or has a prime factor not in the original list. That's your contradiction. So that would be step 3. And step 4 is just stating that the original statement is true. Therefore, there is an infinite number of prime numbers. So going through our steps, step 1 is to make your assumption that the original statement's not true. Step 2, you work through your algebra, your algebraic methods. Step 3 is you use the sentence frame to explain that the assumption wasn't true. So the assumption that blah 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 is not true because, and then step 4 is to say therefore my original statement is true.